Welcome to the third and final part of AP Statistics Chapter 9 review. This is going to be 9.3, which is tests about a population mean. We covered proportions in the last video, so we're going to be talking about means right now. So let's get started. As with proportions, there's going to be a few conditions we have to check. Now, when we were talking about conditions for proportions and for significance tests, we said they were similar to the one for confidence intervals. There was one difference. Here, there's no difference. It's going to be the same as the conditions for confidence intervals for means. So we have a random condition, which basically says, oh, the sample should be random, 10%. It cannot exceed 1/10 of the population size, and large counts are normal condition, which basically says there are three criteria. First, you check, is the population normal? If it is, good job, you're done. Second step, you check if there are at least 30 samples. So your sample size, n, has to be greater than or equal to 30. If that's there, you're done. Now, what you're most likely going to face is the third one because they want to make sure you're actually going through all the steps and doing as much work as you need. And that's when you have less than 30 samples. You have 10. You can still use it for that on one condition. You make a box plot and a normal probability plot of the data. It's going to give you data if it's less than 10, or it's going to say that, or it's going to give you a box plot and normal probability plot. Most likely it'll give you data because that's more work for you to do. But you have to create your own box plot, normal probability plot, and add them to your answer, and then show that there cannot be more than mild skewness. But you do want to err on the side of that it's normal. So as long as there's no outliers and it's not like completely skewed to one side, you can say that it's normal and proceed on. So those are the three conditions. Moving on to actually calculating stuff. So the test statistic. For proportions, we said z is equal to the the statistic value minus the parameter value over the standard deviation. Here, if we use the same method, we're going to get a statistic value of x bar minus the mu naught, which is the parameter value, over the standard deviation, which is going to be sigma over root n. That is the formula for the standard deviation of the population. However, this is in an ideal world, and we do not usually know the population standard deviation, meaning we have to use the sample standard deviation instead. So if we do use the sample standard deviation Sx, we have to replace z with t because it's just an estimate. So that's why it's called t. Our test statistic will be t. And this is our formula for the test statistic. You're probably going to need to know this for the calculations, but you can also use your calculator to do the significance test. I'll show you how, but you do want to write down work like this. Okay, now I'll get into how to do it by hand and how to do it by calculator. By hand, you're going to find the t value, right? And then you're going to use something called TCDF, right? TCDF is basically going to be like normal CDF, but it's for t distributions. Remember, we're going back to confidence intervals where you have t distributions and things like that, and degrees of freedom. We're going back to that. Degrees of freedom, reminder, is going to be n minus 1. So that's probably going to be required for your TCDF. You go to the same place, distributions, and then TCDF. You have your lower and upper bound depending on what your t value is. If it's less than, you use lower bound of a negative really big number, and then your upper bound is t. If it's greater than, t is going to be your lower bound, and a really big number is going to be your upper bound. And then it asks you for your degrees of freedom, and you calculate it that way. You're going to get an area. So what it basically gives you is the area under a t distribution with degrees of freedom blank. You plug that in into your response. And the area under that curve, to the right of t, to the left of t, or if it's a two-sided, which we're going to get into soon, more extreme than t. Now, by calculator. Your calculator has a nifty feature that is the t-test. If you remember from last video, we talked about proportions. We did a one prop z test. If you go to statistics and stat tests, there's a one prop z test. That's for proportions because one prop kind of gives it away, proportion. The t-test, on the other hand, is for means. And there's two ways you can do it, just like with confidence intervals, with data or with stats. With data, it gives you the data table. You plug in the data, or you plug it into a list, and then you use that list in your t-test. If you do it with stats, which is the easier way, you're going to need the mu naught. You're going to need the sample mean, sample standard deviation, and everything. Sometimes you're not given all that. You have to use data if you're given data. But this is probably the way you're going to do it. And then for calculations, you write the t statistic, you write t-CDF, and you find the p-value using that. That's going to be your work. But to double check you have the right answer, you use t-test. All right. Now, usually this is where I give you an example and start talking about how to write an example and solve it, and then I get back into some more stuff. We're not going to do that though. Instead of doing an example for one sample t-tests with means, because we did a very similar one with proportions, I'm actually going to save an example for a bit later when we talk about a bit more complicated topic, a bit different at least. It's not, because usually for means it's going to be very similar to what you write for proportions, and I'll show you what you're supposed to write for means in a little bit. But first, I'm going to go through the rest of the topics. Then I'm going to show you an example on a different topic. Okay, just like with proportions, we have two-sided tests that we can do. It's going to be the same thing where you multiply the area by 2. Let's say you have a mu naught of 6 and a sample mean of 6.3. And your original alternative hypothesis is, so your null hypothesis is that mu equals 6. And then obviously you have to define what mu is. But your alternative hypothesis is mu is not equal to 6. You're not specifying which way. It's a two-sided alternative hypothesis. Now, if you get this sample, your t-value, once you calculate it, is going to be positive. It's going to be on this side because 6.3 is more than 6. So if you were to draw this, that's 6. Your t-value is going to be here, and you're going to get that. Once you get that area, you're going to multiply by 2 because it can also be below. In this specific sample, it was above, but it can also be below because we're using two-sided. So you multiply that probability by 2, and then you compare that to the alpha value. So that's basically what you do for a two-sided test. For confidence intervals, same thing as with proportions. You basically use the sample mean you get to construct a confidence interval. If you happen to reject the null hypothesis, you're probably wondering what the actual parameter would be. So that's when you create a confidence interval. If you have a given alpha in the problem, let's say alpha is 0.05, your confidence interval is going to be 1 minus alpha percent. So 95%, for example, is going to be for 0.05. These two tell you very similar things. This tells you whether or not to reject the null hypothesis. This tells you what the actual parameter would be. So they don't tell you the same things, they tell you similar things. They have similar information, and sometimes you need both to get the full picture. Here is where the fun starts, paired data. So if you remember back to chapter 4, when we were talking about samples and experiments and all that fun stuff, we talked about matched pairs experiments. So a matched pair is basically when you basically have the same individual taking both treatments in a random order, and that data is then used to analyze stuff, to make inferences. So this is with experiments. That's kind of important. It doesn't really change the calculations that we do, but it changes how we format our answer. So here we have, let's do an example. You have plants, right? And you have one with fertilizer, one without, and you want to find the height. Let's say there's a change in height. So you can't say my null hypothesis is that you can't say that the mu of the fertilizer is equal to the mu of the no fertilizer. That's not a valid hypothesis in this scenario. What you say is mu d equals 0. I'll talk about what exactly that means. But mu d is basically going to be the mean difference, the difference between the two data points. So you're going to take fertilizer minus no fertilizer, and that is going to give you some value, the difference. And then when you take the mean of that differences, of all those differences you get, that is going to be your mu d. So you're basically combining two sets of data into one set of data that you can use to compare. Your alternative hypothesis then, you're saying, oh, the fertilizer is going to make it grow much taller. So mu d is greater than 0 because fertilizer minus non-fertilizer should be greater than 0 for the fertilizer to be greater than the non-fertilizer. That's going to be your alternative hypothesis. Obviously, define mu d. That's going to be the mean difference between the fertilizer and non-fertilizer plants. All right. I'll talk about an example of paired data. And that will be our example for this video. But before that, I'm going to talk about one last concept, and that's factors that influence the sample size required. This also goes the other way around, factors that influence the power. This is where we actually talk about power. So there's three main factors that influence sample size. As you might imagine, the significance level, alpha. Two is something called the effect size. And effect size is basically going to be the difference between the null parameter and the actual parameter that we're trying to detect. So this goes back to power, where we say, oh, when we were talking about proportions, we said, let's say the null parameter is 0.6, the actual is 0.8. Let's say we somehow know that. Can we detect that the actual is 0.8 and reject the null hypothesis? Can we do that? That's the power of the test. It becomes more powerful as the effect size increases, actually. Um, because there's a larger difference, it's easier to detect a larger difference. So in an example with means, let's say the mu is 6, and that's the null hypothesis. The null mu is 6, but you somehow know that the actual mu is going to be 9. The effect size, therefore, would be 3. So the larger the effect size, that's going to impact the sample size required to conduct a successful significance test. And 3 is going to be your power, the power at that certain effect size. So this goes the other way around too. Power is influenced by these factors. It is influenced by the effect size, but you have no way to control the effect size because you don't know that. You don't know the actual parameter. That's just a hypothetical that we know it. So technically it's influenced by effect size, but you can ignore that. That doesn't really affect the power that you can control. Significance level, yes. If you have a larger significance level. So this is 0.5, 0.05, let's say. If you have 0.10, 0.1, basically, your power is going to increase. And I'll show you a small diagram of why that's the case. So this is 6. And if you were to increase that to be 9, because you know the actual is 9, and let's say that the it's going to be 0.5 up here, right? That means here. Let's say it's down here. That means that the same line down here is going to have this big of an area. But if you increase the significance level to 0.1, that's going to increase the area down here because the line moves and therefore covers more area in the actual. Now let's talk about how sample size affects it. The larger the sample size, the higher the power. And the reason why is because what does sample size affect? It affects the spread of the distribution. So a larger sample size basically means it's going to look more like this. There's going to be less extreme values. So imagine something like that, right? So if there's going to be less extreme values over here, your 0.5 has to physically move this way, 0.05 has to physically move this way such that it includes exactly 0.05 of the area. If it was still over here, like it was before, it's not going to include 0.05 of the area because there's more extreme, there's less extreme values. There's more when you get here, which is why the same line going down will cover more area, just like if you increase the significance level. More often than not, you're going to want to increase the sample size if possible, because increasing the significance level, while it does increase the power and therefore decrease the probability of getting a type 2 error, it also increases the probability of getting a type 1 error, because the probability of getting a type 1 error is just alpha. So when you increase alpha, you're going to increase that probability. All right. Finally, we get into our format for how we structure a response. Same thing as proportions. We want to test at the alpha equals blank level, usually going to be 0.05, but it could vary. You write your hypotheses and explain what the parameter is. If conditions are met, we will conduct a one sample t-test for means at the alpha equals blank level. This is the only thing that's different. Instead of a one sample z-test for proportions, it's a one sample t-test for means. You check your conditions, random, 10%, and large counts are normal. You do your calculations, and you write your concluding statement. Looks very similar to proportions. But that's where we're going to diverge a bit. We're going to talk about paired data, and we're going to do an example with that. And that has a little bit of a different structuring, which is why I wanted to use that as an example so you can see how to structure that. Okay, let's look at our example. Looks pretty long. We've done this before, but basically what it's saying is coffee, we're seeing how coffee affects depression. Basically, if you have people who depend on coffee, you take away their coffee, are they going to be more depressed? So what they did was they gave the same subjects caffeine and placebo. So since it's the same subjects, it would be a paired data set. If the people drank coffee before and then they suddenly took a placebo, would it make them more depressed? So the depression for the caffeine for each subject was measured. The depression for the placebo for each subject was measured. And then you subtract placebo minus caffeine because what you expect is that the placebo will be more depressing or more depression would come after you drink the placebo rather than drinking the caffeine. So you have that data set. Now you have to actually write the response to it. We want to test at the alpha equals 0.05 level. Did it say that? No, it didn't. So since it didn't, we assume that it's 0.05. What's our null hypothesis? That's going to be that the mean difference is equal to 0 because the null hypothesis, we're assuming that everything's the same, there is no difference. The alternative hypothesis, on the other hand, is going to state that the mean difference is going to be greater than 0 because we expect the placebo to cause more depression than the caffeine. And now we have to define our parameter where mu d is the difference in depression scores for subjects like these. That's an important thing for subjects like these. That means that this is an experiment. We have to acknowledge that this is an experiment rather than a sample. It's not going to be a random sample. And that's going to affect our conditions as well, which I'll get to in a minute. If conditions are met, we will conduct a paired t-test, not a one sample t-test. It's going to be a paired t-test for means at the alpha equals 0.05 level. Okay, random condition. Now this isn't going to be a random sample because we're not doing a sample here. We're doing an experiment. So our random value is going to be random order of the caffeine and placebo. So that's going to be what we're testing. 10%? Wrong. We don't need a 10% because we're not doing samples. The sample size cannot be less than or equal to 1/10 of the population. We don't need a 10% condition. You can just write NA or you can just not do it. I would write NA to show that you actually know that you don't need a 10% rather than letting the readers think that you don't remember there was a 10% condition in the first place. And finally, our large counts are normal condition. It's a bit weird, but we're gonna have to use a box plot and a normal probability plot. These are the two plots. As you can see, there is some skewness, but it's not enough skewness that we want to call it not normal. The normal probability plot doesn't really look like a line, but you can kind of make out a line if you look really hard. That's what matters. So you want to err on the side of normal because you really want to do this problem, even if you don't. But they're going to make you do this problem anyway. So we can say that it looks pretty normal. And so all our conditions are met. We can go ahead with the calculation. This one's going to be a bit different because it's paired data. So what you're going to do is you're going to go back to t-test. You go to stat test, you go to t-test, and you have to click data at this time. And your mu naught is going to be 0. Your list wherever you enter the data. And your alternative hypothesis is going to be greater than in this case. And what you're going to do is you're going to get a p-value. I will not spoil that for you now. You can calculate it if you want. But you're also going to get a t-statistic. And as an exercise for you, you can show your work for calculating the t-statistic. I'm just going to write down what I got. It's going to be t equals 3.53. And also you have to note that the degrees of freedom is going to be 10 because it's 11 minus 1. 11 is it's not really the sample size because remember it's an experiment, but 11 is the number of participants. So you're going to use a degrees of freedom of 10. Now, given these two things, you can use TCDF. So go back to stat, go to distributions, go to TCDF, and you're going to have a lower bound of 3.53 because it's positive. So we're looking at above 3.53. So lower bound is going to be 3.53. Upper bound is going to be a really, really large number, like infinity. Degrees of freedom is going to be 10. And you're going to get a p-value of 0.0027. Now, you probably also got that if you did t-test, and that's what you should have gotten if you did t-test. But that's our answer. Box it if you want. Now, how do we write our concluding statement? What we're basically going to say is because p equals 0.0027 is less than alpha, which is equal to 0.05, this means that it's less than that. It's small enough that we can consider it statistically significant. We reject H naught, the null hypothesis, and there is convincing evidence. Remember, not there is evidence, or don't say oops. Don't say we accept. Say there is convincing evidence for the alternative hypothesis for subjects like these. Don't forget that because we need to acknowledge that this is an experiment, not a sample. So always write that in your concluding statement. So that's that. That is the example. And there's just one more thing, or actually two more things to go over means. Not really, it's kind of like an end of the chapter thing. So I don't really have an extra slide for it. So I'm just going to talk at you while this is still on the screen. But one thing is that you need to be aware of sample size. So if you have a sample size of 2,000, even if there are at least 20,000 people in the population, if you have a sample size of 2,000, be wary of statistical significance because even a small difference can be considered significant by a significance test if the sample size is large enough. You have 2,000 people, you need to be careful. You need like a low enough alpha value, like 0.00001 for it to actually be considered very significant for a very large sample size. So basically what it's saying is statistically significant difference does not necessarily mean it's practically important. It's just a significance test. Second thing to note is called multiple analyses. Basically, if you run multiple tests at once, you're going to introduce more error. You're going to increase the probability of a type 1 error because you're basically doing multiple tests at some alpha level. Well, those alpha levels are going to add up and the total probability is going to be the sum of those alpha levels. So if you do it at 0.05, which is completely fine for one test, if you do 20 of them, you're going to get a very big probability for type 1 error, and it's almost guaranteed that you'll make one. Of course, it's very likely. It's not guaranteed. That's not how probability works, but it's very likely. It's implausible that you won't make one. Let's say that. So even what you can do to make sure that doesn't happen is use chi-squared. We didn't get into that, but basically that takes multiple tests into one, so it doesn't really increase the probability for type 1 error that much. So that's it for chapter 9. Congratulations, we're done with chapter 9. This is 9.3, which is the last section. So we basically covered tests for population means, putting a whole end to significance tests for now. Chapter 10 is going to get back into significance tests and things like that, which with two populations actually. So I'll see you for chapter 10.